Hello, and thank you for joining. My name is Carrie Gardner. I'm the Product Marketing Manager for FDM here at Stratasys, and I've had the pleasure of working very closely with the materials team. Today's webinar, Achieving Your Full Application Potential, the FDM Material Ecosphere, is the first in a quarterly series of webinars about FDM materials. We are excited to share today more information on the vast FDM material portfolio, hopefully making you aware of the different categories and types of materials offered. And stay tuned for our next webinar at the end of June. I have a few housekeeping things before we start. Please use the question chat function at any point during the webinar, as there will be a live Q&A with our presenters at the end. And secondly, this webinar is being recorded and will be available for reference on stratasys.com under resources. For today's agenda, we will give an overview of FDM technology, including a discussion about Stratasys' repeatability and reliability. Then we will delve into the FDM material portfolio and the materials testing that Stratasys uses. Wrapping up today's session, we will provide an understanding of how the various materials connect to application needs. So we'll conclude this webinar with some case study and real-world examples and ideas to fuel some of your 3D printing ideas. But first, let's meet our experts. Today's session will be presented by Nathaniel Clausen and Zach Gunnelson. Nathaniel is a product manager for FDM materials here at Stratasys. Nathaniel has been with Stratasys since 2017, focused on the Fortis 450 MC and F900 materials. Nathaniel has been working to grow the materials ecosystem through the launch of new products such as Antero 800NA and Antero 840 CN03. He also leads the development of our partnership programs and the validated materials product portfolio. And Zach is an application engineer specializing in the FDM materials portfolio. He holds a degree in mechanical engineering from the University of North Dakota with a focus on materials and manufacturing processes. Zach has recently authored a white paper on the fatigue performance of Stratasys FDM materials and has played a key role in launching several FDM materials for the Fortis 450 MC and F900. I want to thank both of you for sharing your time and expertise. And with that, I will pass it along to Nathaniel.
Thank you, Carrie, for that introduction, and thank you everyone for joining. Today we'll be going over the Stratasys technology portfolio and focusing on our FDM technology and material options. Stratasys has the best-in-class portfolio for additive technologies, including polyjet stereolithography, our Origin P3 and SAP. Additive technologies. Today we'll be focusing on our industrial FDM capabilities and the various materials that can be run through these systems. So FDM technology is the ability to take polymer filaments, run them through a FFF or fused deposition modeling printer where they are heated and extruded based on the CAD files or parameters sent to the printer. These files direct the printer to put the polymers in the specific locations to print out the exact part intended. Within the Stratasys FDM portfolio, we have a variety of platforms to meet your application and size needs. On the smaller end, we have the Stratasys F170 and F190CR. These are our smaller FDM printers capable of utilizing our standard and engineering grade materials. We also have the F370 and F370CR, which are slightly larger versions of the F170 and 190CR. From there, we go to a much larger platform in the Stratasys F770. Again, this printer utilizes both our standard grade and some engineering grade materials, but it is able to produce much larger parts. Moving into our higher temp and industrial printers, we have the Fortis 450 MC and the Stratasys F900. These printers are capable of printing both our standard grade and engineering grade, along with our high performance materials. which allows for much higher end applications and in-use parts. And Stratasys recently released our new flagship system in the Stratasys F3300, which gives improvements to both print speed and quality. So looking at where these various printers fit in your application needs. For the most part, when you're looking at your prototyping applications, these are typically smaller parts, looking at doing multiple iterations, really looking at fit, form, function type areas. You're looking at the F170 and F370. If you need slightly better performance, you're getting into maybe some factory floor tooling. You might want to consider the F190CR or the F370CR. This allows for some of our materials that have light loading and some better mechanical performance for those types of applications. And if you're in the need of large parts, either for prototyping or tooling, the F770 is what you're looking for. On the higher end, on the industrial end, we have our Fortis 450 and F900. These two systems have been in the market for several years now and are very well represented, very good performance and history behind these printers, and they are capable of printing the full portfolio of our materials, including our high performance aerospace production grade materials. And then newly released, the F3300 again is the new flagship system, which brings all the capabilities of the 450 and 900 with higher print throughputs, higher quality, and better performance. All right, I'll turn it over to Zach to talk about the repeatability and reliability of the Stratasys systems.
Thanks, Nathaniel. Yeah, let's hop into the repeatability and reliability of Stratasys FDM systems. To demonstrate the repeatability and reliability of Stratasys FDM printers, testing was done for over 1,200 builds across 16 different systems using 3 different materials. And the focus was to find the dimensional precision, mechanical performance, and overall yield of these systems. Starting with the F370, parts that had average features that were smaller than 2 inches showed a average standard deviation of about 12,000 inches, whereas parts that were over 8 inches show a 1/1200th of an inch standard deviation. The Fortis 4050 MC and the F900 systems were a little bit better by showing features that are less than 2 inches of 9/10,000ths of an inch, and the average standard deviation for parts that are greater than 8 inches for the 450 MC being 1400ths, and the F900 being having a standard average deviation of 32,000ths of an inch. To show these a little bit more visually, looking at these graphs, on the left, you can see the F900 system. Over the course of 50 plus builds, you can see that the repeatability of the dimensional stability on these systems is very good, and there's not much deviation there. The image on the right also shows the builds that were performed on the 450 MC, and again, very good dimensional accuracy and dimensional repeatability with these systems. And if you want to learn more about this, you can go ahead and go to that link in the top right. Moving on to the mechanical performance of these systems, the coefficient of variation was analyzed over the ultimate tensile strength of the different various printers and materials. You can see for ASA on all 3 systems that the average coefficient of variation of the XZ printed parts was less than 6% for all 3 printers. And in the ZX direction, it was less than 10% for all printers. For the Fortis 450 MC and the F900, both Nylon 12 CF and Altum 9085 were tested as well. And you can see those trends follow through with the low coefficient of variation in XZ and ZX for both materials and systems. Going over the job and part yield, there's an exceptional job and part yield across all platforms. The job yield was 95% or greater on the F370, and the part yield was 99% on those printers. And for the Fortis 450 MC, right around 88% for job yield, while the part yield was at 93%, and the F900 had a great job yield and part yield of 92% or greater. In these images right here, we can see how the mechanical performance, repeatability, and reliability testing was done. The image on the left is the F900 that was loaded with mechanical coupons that were the Tensile D638 coupons. On the bottom right hand of the left-hand image, samples 1, 2, and 3 are tensile bars that were printed in the XZ direction, and samples 18, 19 were in the ZX direction. And you can see that those are laid out throughout the build platform, so that way we can see that there is continuous mechanical performance throughout the whole platen of the printer. And same thing on the image on the right hand, except for this is for the Fortis 450 MC instead. And now I'll pass this back to Nathaniel to go over the FDM materials ecosystem.
Thanks, Zach. Within our material portfolio, we have 3 categories of materials. Our preferred materials are our highest, highly tested and validated materials for meeting the highest and best application requirements. We have our validated materials. These materials are either Stratasys developed or developed by third-party partners, such as Victrix with our AM200 product. These materials meet the same quality and production requirements, but have slightly less validation and mechanical testing associated with them. And our third tier is OpenAM. OpenAM is a software application that allows customers to utilize any third-party material that is not necessarily part of the Stratasys ecosystem. So if they do have custom or specific material requirements, they can look to acquire those materials outside of Stratasys. So just going into some additional detail on our 3 tiers of materials. So our preferred material are Stratasys developed materials or co-developed materials that have gone through a rigorous integration and testing and validation process. They are fully supported through our sales channel and also through our service agreements. Our validated materials have very, very similar requirements here. They may not be exclusive to Stratasys. Some of these products, some of our partner developed products are also sold into other FFF printers, but they do go through a Stratasys development process to the same requirements as our preferred materials. They're manufactured to the same standards, and they are fully supported through our service agreements and through our sales network. With OpenAM, these materials are outside of the Stratasys ecosystem. So it is a software package that allows customers to utilize third-party materials that are not supported by Stratasys. They can work with third-party materials to develop materials or develop materials on their own. Looking at the Stratasys portfolio, Stratasys has a very diverse portfolio, stretching from your typical standard plastics such as ABS and ASA, your engineering thermoplastics such as PC, PC ABS, nylons, along with a variety of colors and functional capabilities in those materials, along with our high performance materials, where we get into kind of our higher thermal and mechanical capabilities with our Ultim products, our Antero products, and our Victrix AM200. We also carry a thermoplastic elastomer, the TPU92A, which is used primarily for those soft touch applications, applications where you need flexibility in your parts. Looking at our portfolio, as you can see, it was a very diverse portfolio with lots of different types of materials and different chemistries. This image here helps to kind of understand where these different products fit within their capabilities and also within their price. As you look to the lower left, we have a variety of standard polymers, ABSs, ASAs. And as you move up the performance capabilities into your polycarbonates, into your nylons, flame retardant nylons, you start to grow that application space, get into some of those industrial requirements that are needed, such as flammability. And then we move into our high performance segment, which is primarily for aerospace, but has other utilizations in many other applications, such as the oil and gas industry for its chemical compatibility, your higher temperature requirements, and other aspects of the application. So Zach will cover Stratasys material testing and standards that are used to validate our products.
There are several standards within additive manufacturing, with one of the biggest ones being ASTM, or American Society for Testing and Materials. This society generally makes testing standards for mechanical, physical, and chemical testing. And some of the big ones that are followed at Stratasys are the standards for tensile testing, flex, compression, and impact. Another large standard organization is ISO, or International Organization of Standardization. This one generally focuses on creating standards in additive manufacturing, focusing on quality, safety, and terminology. And with those, you have a lot of site ISO standards. For example, ISO 9001, ISO 13485, 27001, 45001, and 14001. And all of those are various levels of certifications for development and manufacturing of 3D systems and materials. All of these ISO organization standards are, or Stratasys has all of these ISO organization standards approved for their facilities. Other common standards within additive manufacturing that Stratasys follows is UL94 flame testing to show the UL94 compliance for our Ultim 985 material, EN 45545 flame testing, which is a European rail flame standard, and we have that for the Ultim 985 and Kimya PC FR materials. And finally, NFPA 130 flame testing, which is a United States rail testing, rail flame testing, and we have that for Ultim 985. Every Stratasys material is tested following the same methods as far as printability and testing goes. And each material is tested for tensile, flex, and impact properties, with some of them also being tested for compression properties as well. Each material is tested in the XZ and the ZX orientation. And with tensile, there are the properties found are the yield strength, elongation, strength at break, and modulus. For flex, it would be the strain at break, strength at break, and modulus. And for the impact, there is both notched and unnotched testing. There's also material-specific testing that can be done for depending on the material characteristics. For example, if you want to find the chemical resistance, we've done testing on that for Ultim 985 and for the Antero products. Some materials will have electrostatic dissipating, or ESD, properties, and we have that testing done for our ABS ESD7, PC ESD, and Antero 840 CN03. And finally, flame, smoke, and toxicity testing has been done for Ultim 985 and for the Antero products. Another material characteristic that is important is the fatigue performance of materials. This is especially important for materials that are going to be used within the aerospace industry, but it's important for any material that might be subject to a lot of cyclic loading or forces that are applied and taken off of a part repeatedly for a very long period of time. The importance of fatigue performance of materials shows due to premature failure of a part if it's under the fatigue stress. For example, if you have a very low stress on a part, but it's just constantly applied and taken off, then that's going to have the part fail prematurely due to that stress building up over time. Stratasys has performed fatigue testing on 3 of its materials, including the Antero 840 CN03, Ultim 985, and Nylon 12 CF. As you can see on the triangle to the right, Antero 840 CN03 has the best fatigue performance, while Ultim 985 and Nylon 12 CF have great material fatigue performance. And then your standard polymers such as ABS, nylon, PET, and PLA will all have decent fatigue performance, but not the greatest. For Antero, it's great for aerospace applications that need to be ESD safe and chemically resistant. For Ultim, it's great for applications that require that FST, or flame, smoke, and toxicity. Nylon 12 CF would be great for any unmanned aerial vehicles, automotive housings, or aluminum replacements. And now moving back to Nathaniel, where he'll go over choosing the best material for your application.
Thanks, Zach. As we've shown through this presentation, Stratasys has a very diverse material portfolio with lots of options based on your application needs. On the following slides, we'll be going through some examples of the different chemistries and showing some use cases, some real-world use case examples of how these materials are being used. Starting off, Ultim 9085. This material is primarily used in the aerospace industry, but has utility in many other applications. It's best known for its flame retardant capabilities, meeting both UL 94V0 and FAR 25.863 certification for flight parts on commercial aircraft. It also has a very high strength to weight ratio, good chemical resistance, and high HDT. With Ultim 9085 CG, we have an AIS package which allows customers to achieve the maximum capabilities of this material in an FDM printer. It comes with a different tip, a T16A tip, which lowers the coefficient of variance to even improve the repeatability and reliability of our systems even further. It has full traceability of the materials, including all the production data, both raw material and filament production data, which is provided on the certificate of analysis with your material, and in a detailed process control document that is used by customers to make sure their systems are operating at their full potential. When utilizing the AIS package, along with the process control documentation, as you can see from the data, you get a significant increase both in the mechanical performance and a significant decrease in the coefficient of variance with this material. This allows customers to expand the application space through the improved mechanical performance of the material. It also increases the repeatability of the system and predictability of the performance of those parts. Stay tuned for some additional announcements related to new materials that will be included with this AIS package. So looking at Ultim 90, real use example of Ultim 9085 material. This use case is from United Launch Alliance. They were looking to reduce their assembly and part count in complicated ducting components that needed to fit within very defined and controlled spaces. With utilizing all the Ultim 9085 material in an FDM printer, they were able to reduce the number of parts needed to create the ducting from 140 to 16 and significantly reduce their part costs. Another example is Great Western Railway. Great Western Railway works to refurbish old rolling stock and update them for modern use. In doing this, many of the suppliers that initially produced components for these various trains no longer are in business, and they need to be able to replace parts and develop and design new parts to fit the new applications for these trains. Utilizing FDM along with Ultim 9085, which meets the EN 45545 rail flammability requirements, and also our PCFR material, they were able to recreate and produce parts to refurbish trains to put back in circulation. Moving on to Antero 800NA. We offer two Antero products, both the 800NA, which is a neat material. It has no additional fillers, along with Antero 840CN03, which is an ESD variant of this material. A PEC-based thermoplastic, which provides high chemical resistance, very good thermal capabilities, very low outgassing, meets all of the flame retardant capabilities, such as FAR 25.863. When looking at the Antero products versus the Ultim 9085, Antero will provide some better fatigue performance, some better chemical resistance and thermal performance compared to the Ultim 9085. But it also has it is a very similar application space. It's really defined by your needs as a customer and your specific application area. Another version of our Antero 800 is our Antero 840CN03. This is an ESD variant of the 800NA. The ESD meets all the same flammability, chemical capabilities, fatigue capabilities as the 800NA, but also includes the ESD performance for use in electronics, electronic housings, in high dust applications where we don't want static charge buildup. A good example of where you would not want static buildup on plastic parts is on the Orion space capsule housing, which is being produced by Lockheed Martin. Lockheed Martin has chosen to use the Antero 840CN03 along with the Fortis F900 printer to produce the panels that go in the docking bay of the Orion capsule. So this is the actual exterior of the capsule that does connect with the International Space Station. We don't want any static buildup that could potentially interfere with the docking process. Moving on to Ultim 1010. Ultim 1010 is a high temperature, our highest temperature thermoplastic that we offer. Typical applications for this material are in carbon fiber layup tooling and also functional prototyping where high temperature is a consideration. One example of a high temperature application for Ultim 1010 is with Boom Supersonic, who use the Ultim 1010 material to prototype and functionally test exhaust manifolds on their new jet engines for their supersonic aircraft. Ultim 1010 met the high temp requirements of being able to withstand the high temperature exhaust coming off the engine for functional testing and design validation. Using Ultim 1010 allowed Boom to save several weeks on the production of the parts to get it into testing and thousands of dollars prior to committing to their final design. PCABS is an example of a general purpose material that is available across all of the Stratasys FDM printers. It is typically used for prototyping, low requirement production, factory jigs and fixtures and tooling. It offers excellent strength, toughness, good heat resistance, and good durability for handling, for repeated handling in production environments. The use case example for the PCABS is with Joe Gibbs Racing. For those not familiar with Joe Gibbs, they are heavily involved in the professional racing circuit. Within the professional racing circuit, there is a lot of iterative designs that have to happen week to week between races. The use of FDM, PCABS, and other materials allows them to iterate very quickly. They come up with custom designs to meet specific track requirements, including customized dashboards and other applications within the race cars. They have very fast turnaround times in which they have to produce these parts, get them installed into their cars and off to the tracks. Using FDM and a variety of different materials on their platforms, they can quickly iterate and make sure that cars meet the standards for those races and in top performance condition. Looking at some additional general purpose materials, ASA is a very common thermoplastic used in a wide variety of applications. It has very good UV stability. We offer a variety of colors in this material, and it is available across all of our printing platforms. It's typically used in various prototype applications, a lot of low requirement jigs and fixtures and factory floor applications. It can also be used in a variety of low volume production. A good example of using ASA with the Stratasys F170 is by Bilo in France. Produces custom pick and pack equipment for warehouse applications. Utilizing the F170 with ASA, they are able to customize their equipment to meet their customer needs for their specific warehouse applications. Another example of utilizing ASA with our large format printer, the F770, is with Daikin. Daikin needed to be able to produce and test nozzles that redirect airflow in a test chamber. The size of the F770 allowed them to produce these as a single piece and customize them to their needs. This saved them a considerable amount of costs versus traditional manufacturing of these types of components. One of the most versatile materials in the Stratasys portfolio is the nylon 12CF. This is a chopped carbon fiber filled nylon material that is 35% by weight. The addition of the carbon fiber to the nylon 12 material allows for additional strength and stiffness, allowing it to be used to lightweight components as an aluminum replacement. It also, as earlier noted, has very good fatigue resistance. This material is typically used in a variety of factory floor applications and tooling, repeated use parts, functional prototyping, and also in final production. Good example of how this material is used on the factory floor is with General Motors. General Motors was working to develop their assembly lines for their Chevy Bolt electric car. They were able to utilize the nylon 12CF due to its stiffness and strength in a variety of places on the manufacturing floor, including reducing the weight of a conveyor pellet design to reduce the amount of maintenance required due to the weight of the tooling. Looking at how smaller businesses can utilize both FDM and specifically the nylon 12CF material is through final part production. Looking at Utah Trikes is a small company that produces small batches of their trikes and bicycles. They were able to utilize the nylon 12CF due to its strength and stiffness and the final design of their trikes. This allows them to bring these trikes to market much faster at a reduced cost over traditional production, given their low rates. Final material that we will be showcasing today is our polycarbonate. Polycarbonate is a very common use material used in a wide variety of applications. It is best known for its impact resistance and heat resistance, along with its dimensional stability. We do offer three colors, white, black, and red, to be used typically in manufacturing aids, jigs and fixtures, production parts, and functional testing. Example of how PC was used is from Bell Helicopter. They like the temperature, performance, and hardness of the material, along with the impact resistance to conduct functional testing of a wiring upgrade for the Osprey. This allowed them to customize and build the wiring assembly prior to installing and testing in the aircraft, saving them quite a bit of time in iterations of matching the Osprey design with the upgrade. This saved them quite a bit of time in matching the upgrade to the existing framework of the Osprey.
Thank you, Nathaniel and Zach, for all the great information. As a quick reminder, for anybody looking for more information on any of the Stratasys materials discussed today, please refer to our website at stratasys.com. Each material webpage has an option for you to download a materials data sheet for more information. With that, let's open this conversation up to questions from our audience. Again, please use that question function to add any questions for our experts.